Hello everyone, this is the third lecture of the series from high school to physics, and in this lecture I will be talking about functions or mappings. So in the previous lecture we have learned about what is a relation. We have learned about relation. What is a relation? If there is a set A and there is a set B and there is a set A and there is a set B, then A cross B is the Cartesian product of A and B, and a relation is nothing but a subset of the Cartesian product of A cross B. So yes, this is a relation. Our element in relation is like this. So A belongs to small a belongs to set A and small b belongs to set B, and this tells that A and B are related. So yeah, this is relation. So a function or a mapping is also a relation. It is also a relation, but it has a special type of condition, right? So let me tell something about it. So you can think as function, yeah, you can think function as a machine. So this is a function. You give something input and the function gives you the output. Okay, so this is a function. A function is nothing but a machine that gets something as an input and gives something as output. So the input is nothing. What can you give as an input? You can give any elements. Suppose you are giving element A as input and element A belongs to a set A, and the function gives an output. Let the output be B, which belongs to set B, and if the function is f, then we say that the function of A is B. So we can write like this, or we can also write like this, that a function f is defined from A to B. Okay, we can also draw a diagram that if this is A and this is my set B, then a function relates the elements of A to elements of set B, and this has a special condition, like when I'm saying that when I'm giving an input to a function, it gives an output. That means the output is unique output. Okay, so whatever you give as input, it will not give multiple values as output. It will give a single value as output. It can be a number, it can be a scalar or a vector or whatever it is. It will give a single valued output. It will not give multiple outputs. So f of A, suppose f of B is B1, then f of A cannot be B2 also. Okay, yeah. So this is the definition of a function, that it is a relation. Function is a relation from set A to set B that assigns each elements of A to exactly one element of B. Okay, so that for every A belongs to A, there exists a unique B belongs to B, such that f of A is equal to B. So this is a function, and you let me just give you some types of function. I will tell you about some types of function. I will tell you about inverse of a function, but before that, let me give you a let me tell you about some terminologies. Okay, so suppose I have a function here. I have a function that relates A to B. Okay, the set A to set B. Then this set is called the domain of the function, domain of f, and the set B is called the range of the function. Okay, so yeah, so A is called the domain of a function and B is called the range of a function if the function relates elements of A to the elements of B. Okay, and for every element of A, there exists a unique element in B. Okay, so let's see some examples. Suppose we have a set A which has 3 elements, 1, 2 and 3, and there is also B where there are also 3 elements. Suppose X, Y and Z. Okay, so a function can be like this, like it is relating 1 to x, 2 to also x, and 3 to z. Okay, so we get that f of 1 is x, f of 2 is also x, f of 3 is z. Okay, so it is a valid function because it is giving a unique output for every input from its domain. Okay, so this is called the range of f, this is called the domain of f. Okay, so let me give a few more examples about this. And this is a function from a finite set. Okay, and let me give you another example, like a linear function. A linear function. What is a linear function? You can linear function is, its domain is R, or the real number, and its range is also R, the set of real number. So you can define any linear function like this: f of x equal to mx plus c, where m and c are numbers, constant numbers. If you are aware about coordinate geometry, then you will know definitely that this is the equation of a straight line, and that is why it's called the linear function. Okay, an example can be this, like f of x can be 2x plus 3. Okay, some another function g of x can be minus 3x plus 4 over 27, like this. Okay, so this is any function with this structure, mx plus c, will give you the linear function. Okay, so let me give you another example. There can be a quadratic function. What is a quadratic function? It's nothing but a quadratic equation. Okay, so there can be a function f such that it gives an output like this: ax square plus bx plus c. So if it gives an output of this form, then it's called a quadratic function. And if you are well aware of quadratic equations, if you have done them, then you know that this is a quadratic equation where a is not equal to 0. Okay, why is a not equal to 0? Because if a is equal to 0, then this term will get vanished and it will be bx plus c. It will become a linear equation. It will have the same form as this one. Okay, so a is not equal to 0. This is an important thing. And also this is also a function. Its domain is the set of real numbers, and its range is also the set of real numbers. Okay, and this means nothing but that x belongs to R, and ax square plus bx plus c also belongs to R. Okay, yeah, so this is quadratic function. There can be other functions as well. Okay, so yeah, so you can say that there can be a function like f of x comma y is equal to x square minus 4xy plus y plus 3. So this can be a function. This is a multi-variable function. It has two variables as its function, x and y. It depends on x and depends on y. So this function is nothing but it goes from R2 to R. What is R2? R2 is nothing but it is nothing but the Cartesian product of two sets of real numbers. So x comes from this and y comes from this. So a Cartesian product of any two real numbers is like this. Okay, so this is what the function is depending on, x comma y. Okay, so it depends upon x comma y, and the value x square minus 4xy plus y plus 3, this belongs to the value r. So yeah, so that's why the function goes from r square to r. Okay, so yes, these can be some examples of functions. And yeah, so now I will be talking about types of function. Okay, so how can we differentiate a function? We differentiate between some functions and like those, some important types of functions. We can classify functions in many ways, but I'm going to talk about an important classification of functions, and let me just write them. The first one is injective function. or it is also called one-to-one. Injective functions means that suppose we have a domain A, a function is related from A to B, and one-to-one means that for every element of A there exists one unique element of B. Like this, for every element of A there exists one there exists a unique element in B, such that no other element in B can be equal to can be related to that same element. Okay, so yeah, so I can say let me give you an example. Suppose A has 3 elements and B has, suppose A has 5 elements. Okay, and B has 6 elements. Okay, so suppose 1 is related to 2, 2 is related to 3, 3 is related to 1, 4 is related to 4, 5 is related to 6. So this is a one-to-one function or an injective function, because f of 1 is equal to 2, f of 2 from B, like I'm writing like this, f of 2 is 3 from B. Like this you can write, see that every element of A has a distinct, as a unique element in B related to it, and such that you can also write this, if f of A1 is f of A2, that means an element A1 from the domain of A and another element A2 from domain of F, if they are same, this can only happen for an injective functions if A1 and A2 are same. If they are the same element, then only they can be related to the same element, or else if A1 is not equal to A2, if A1 or A2 are different, then the element in the range, the element in B they are related to, are not the same. Okay, so this is one-to-one function or injective function. Okay, so yeah, you can rewatch this if you want to. And there is also another type of function called a surjective function. Surjective functions, or it is called onto function. What is surjective? See, before you saw that in one-to-one, at the example that I gave, that there is an element in B, 5, fifth element, it's not related to any element in A. Okay, so this is not surjective. A surjective function is such that it connects to every element in its range. So there is no element in its range that is left, okay, that is not related to an element of domain. So let me give you an example. If there are A is the domain and B is the range, and 1, 2, 3, okay, 4, B has 1, 2 and 3. Then this is a surjective function because f relates to every element of B. No element of B is left. Okay, so this is a surjective function. And yeah, so this is a surjective function or onto functions. Okay, and now we will have a third type of functions, which is called the bijective function, and that is nothing but surjective and injective. So when we have a surjective plus injective, if a function has both the properties, if they both have both the properties, then it is called a bijective function. That is one-to-one and onto. Okay, so this is called a bijective functions. I will be telling you in a minute why bijective functions are very important. Okay, so an example of a bijective functions is nothing but this 1, 2, 3 and 1, 2, 3. Okay, so this is a bijective function. This is a bijective functions because every element of A is related to a distinct and unique element of B, and no two element of A goes to same element of B, and every element of B is related to any one of element of A. Okay, so this is a bijective function or one to one and onto function. Okay, so yeah, and one property that you can see here, that for a function to be bijective, its domain and its range both needs to have same number of elements. Okay, so the number of elements in domain of f, that is A in A, has to be equal to the number of elements in the range of f. Because if there is one extra element in A, then for it to be a function or one-to-one function, 4 needs to be related to any one of B. But if 4 is related to 3, then 2 and 4 relates to the same element, so it's not one-to-one anymore. And so just like this, there cannot be one extra element in its domain and also in its range if it has one extra element, fourth element in its range, then it has to be related to any one of the elements in A. So if it is related to 2, then you can see that 2 gets multi-valued, so it's not a function anymore. So yes, so that's why the number of elements in the domain set is equal to number of elements in the range of the function of a bijective function. And you can see that, just let me draw that once again. You can see one thing, that a function goes from A to B and it has a unique output for every unique input, and it covers every element of its range. So I can define another function that goes from B to A, and that is called, let me call this G, function G. And function f goes from A to B and function g goes from B to A, such that g is exactly the opposite function of f. That means that g of f of 1 from A will be 1 from A. Okay, so what do I mean? That f of 1 from A is equal to 1 from B. So g of 1 from B will be just exactly opposite than f of 1 from A, and it will give 1 of A. So you can say that we can define another function g and from B to A that exactly opposes f, and because of that g is called the inverse function. G is called the inverse of f, and it is often written as f of f inverse, like this. And why can we define inverse function in only the case of a bijective function? Because look, a function has to be single valued. So a bijective function only guarantees that the inverse function will be single valued. So if we have, suppose we have a surjective function like this one, a surjective function, you cannot define a inverse function that goes 2 to back to A, and there are two elements that can be reached from 2 to A, and so it gets multi-valued. So there cannot be any inverse function. And in the case of one-to-one function, if there is any left out element in the range, then you cannot define a function, because that element will go where? It will not give any element back to A. So that's why inverse functions cannot be defined on surjective or injective functions, but they can only be defined on bijective functions. Another important thing is the pre-image. What is a pre-image? Pre-image is, let me give you an example. Suppose we have 1, 2, 3 and x and y. And z. So this is a function, and this is a function f. So f of 1 is x, f of 2 is y, and f of 3 is z. So pre-image of x with respect to f is 1. So it tells nothing but the element from it came. Okay, so this is the pre-image. And there is also one thing I would like to tell you, that the composition of two functions. Suppose I have a function f1 of x, let it be a linear function ax plus b, and f2 of x, let it be also a linear function cx plus d. Okay, so these are two functions, and the f1 goes from r to r, f2 goes also from r to r. So this is r, f1 takes r to another r, and f2 also takes r to a different r. Okay, so you can also, so the composition function f1, this is the composition sign. This is from r to r also. Okay, because it tells you that if an element of r, that is the domain, and f2 first acts on it, then on the result f1 then acts on it. Okay, so this tells you that suppose this is the domain r, f2 first acts on it, it goes to another r, and then f1 again acts on it to give another element of r, and together we can write that this is nothing but f1 composed with f2. The example that I gave, f1 of x is ax plus b and f2 of x is cx plus d. f1 composed f2 of x, this is nothing but f1 of f2 of x. Okay, so f2 of x is cx plus d, so let me write that, and f1 of cx plus d is nothing but a of cx plus d plus b, that is acx plus ad plus b. Okay, so if you did not understand this step, this is nothing that I replaced f1 of x here. We had f1 of x is ax plus b. I replaced x with cx plus d here. So I replaced x with cx plus d. So that is what I did here. Nothing fancy. Okay, so this is a composition of a function. So let me give you another example. Let me give you another example. Suppose I have a set A, and if there is a function from A to B, and there is another function from B to C, that is G, let it be G, then we can define a function that goes from A to C, that is G composed after F. Because F acts first on an element of A, then it takes that element to somewhere in B, then G acts it to go to C. So this will acting from A to C. Okay, so this is how composition of functions work. Okay, so let me see the note if I have missed anything. Okay, so let me give you some examples of inverse function. Okay, so inverse functions are only available for bijective functions. So let there be a bijective functions from suppose r to another r. I am giving an example. So there will be an inverse from back to r. So let f be ax plus b. Then f inverse is something such that if f inverse acts after f, then it will return x itself. Okay, if f inverse acts after f, then it will return the element itself. So it tells nothing that if there is an element here, f takes it to here, and then f inverse takes it back to its original position. Okay, so yeah, so can you guess any f inverse that can take x back to that can take ax plus b back to x? So you can write it like that. So f inverse is ax plus b, f inverse of x plus b back to x. So now we have f inverse of ax plus b to x. So how will we determine what is f inverse of x? It's pretty simple. We will just change our variables. We will just substitute our variables. Let ax plus b be y, and then x will be y minus b divided by a. So f inverse of y will be y minus b divided by a. Now we can substitute y equal to x, because it doesn't matter whether I am writing y or x or z, as long as it is this, it has the same combination. So we know that f inverse of x is x minus b divided by a. So from fx equal to ax plus b, we got this. Let's just check that if f inverse acts, when f inverse acts after f, it gives identity, it gives the same element or not. Let's see. F inverse of f of x, this is equal to f of x minus b by a. I did nothing, but I just replaced x here with f of x. Okay, and then I will be writing f of x as this one. So f of x is ax plus b. So you can clearly see that minus b and plus b cancels out, and there's ax by a, and as a is not equal to 0, and I forgot to tell you, but if a linear function is like this, then a has to be not equal to 0 for the same reason as the quadratic function. Okay, so let's suppose that a is not 0, so this means that it is x. We can cut out a from both the halves, and yeah. So our composition works, and we have defined we have found out inverse function of f. So this means that f of x, where is my f of x? This is my f of x. This means that f of x is a bijective function. And you can clearly see that for every x there exists a different ax plus b. So it is 1 to 1. And for every element here, every element y, there exists a unique element here. So it is also onto that every element is covered, and that is why f inverse can be defined here. Okay, so yeah, this is the inverse of a function and composition of a function. And there can be also different functions here, and I'll not be explaining all functions here. It's not possible to explain all the functions here. If you have a particular problem about functions, then you can definitely write down in the comment section, or you can mail me. I'll be putting my email address at the description of the video. So yeah, this will be all for today, and yeah, bye. This is end.